All right, I'm going to start. So yesterday, I talked about sublinear time algorithms for a bunch of examples, such as diameter of a point set, estimating the degree of a graph, estimating the number of connected components in a graph, and MST. Today, what I want to talk about is paradigms that have, under which we've developed a whole slew of sublinear algorithms. Okay, so I'm going to give you kind of two paradigms. They kind of both fall under the same, I mean, there's a place where they have a similar starting point, and then they kind of have very different approaches, but both of them have achieved a whole bunch of sublinear algorithms. Okay, so kind of yesterday was examples, and today is kind of techniques that are somewhat general. And then at the very end, if I have time, then I will talk about a property testing result, just to give you a different flavor of types of results. Okay, because everything we've talked about has been sublinear time approximations of combinatorial optimization problems. And I do want to talk about a different type of approximation that we've been considering. Okay, so more specifically, I'm going to mention something called the Oracle reduction framework. This is a big name for something that's a fairly simple idea, like it should be sort of obvious almost. But I just want to say within the Oracle reduction framework, then we're going to have ways of implementing the Oracle. One way is going to be by taking parallel algorithms, or actually that should say distributed algorithms as opposed to parallel in sublinear time. And the other way we're going to talk about is taking greedy algorithms and trying to simulate what they would have done on the piece of data that I care about in sublinear time. Not the whole answer, but just the part that I care about. Okay? Okay, and then we'll do property testing applied to the monotonicity problem at the very end. Okay, so what's the Oracle reduction framework? It's kind of, I mean, I want you to understand where we're putting in these oracles. It's a very simple plan. We're just going to use sampling to estimate the value of our combinatorial optimization problem. So if I want to know, like, let's take a specific example of vertex cover. Vertex cover, we all remember what vertex cover is, but if not, it's here. It's a subset of V that touches every edge. It's NP hard. You can get a 2 approximation of vertex cover based on the relation between vertex cover and maximal matching is one way to do it. And we're going to do it that way later. Okay, so, but this is an example problem. And I want to just say something about what could we hope to do in sublinear time for vertex cover. Well, nothing we're going to do is going to get you a multiplicative approximation that's like true blue vanilla multiplicative approximation, because if you have a graph with just one edge, you're never going to find it. So you're not going to be able to get something within a factor of 2 of that thing. Okay, or a factor of 5. But if I give you epsilon n additive error, okay, then you don't have to find that. All right, so you need some additive error when you're talking about sublinear time. And of course, you still need, you also are going to need some additive error because as far as multiplicative goes, you're going to need some, going to need to allow some multiplicative error because multiplicative error less than 2, it starts to become hard to do. And, there's all sorts of lower bounds, computational lower bounds for approximating vertex cover to within constant factor. So depending on which assumption you want to use, there are different numbers. Okay, so, but, so sort of, let's go for a 2 multiplicative approximation, but I'm also going to give you epsilon n additive error because we need to sample and we're in sublinear time. Okay, so we're saying that y prime is an alpha epsilon estimate of y if y prime is between y and alpha y plus epsilon n. That's the kind of, so, I mean, you don't really need to worry about the parameters, just multiplicative plus additive, both kinds of error. All right, and this particular notion of an approximation is good for minimization. You'd have a different notion of approximation for maximization problems. Okay. And now the interesting thing is you can get constant time alpha epsilon estimates for vertex cover on sparse graphs. Okay, and The way we're going to do this is use this oracle reduction framework. Okay, this is a really, really simple idea. Okay, we're just going to construct an oracle that tells you if node U is in the vertex cover. I didn't tell you how yet, but let's say you have this oracle that tells you if node U is in the vertex cover. Then what you're just going to do is pick a random node, see if it's in the vertex cover. Yes, it's in the vertex cover. No, it's not in the vertex cover. Pick another random node and estimate the fraction of nodes in the vertex cover. Okay, that's it. It's the simplest thing, right? All right, so if you had a perfect oracle, you could estimate the size of the vertex cover to within epsilon n. Okay, and that's what I mean by oracle reduction framework. It's that simple. Okay, but because now I'm going to show you how to implement the oracles, and I just want you to understand how we're going to use them later. That's okay. So, and that's the big question. How do we implement the oracle? And I'm going to show you 2 ways to think about it, or 2 ways that have been somewhat successful in doing these things. All right, so the first one is to sequentially simulate the computations of a fast distributed algorithm. Okay, and we'll see, and this is an idea of Parnas-Ron, and it's referred to as the Parnas-Ron reduction often. Also, it's a simple idea, but it's been very powerful. Okay, another thing that you could do is try to figure out what would the greedy maximal matching algorithm do on your particular node U. Would it have put U in the maximal matching? Why maximal matching? I'll get to that in a minute. But maximal matching is the one heuristic that gives you a 2 approximation for vertex cover. And so we'll talk about that in a second. But that's another option, is try to figure out what would greedy do for your node U. If it would put it in, great. Your oracle says U is in the vertex cover. Okay, so let's talk about distributed algorithms first. This is the easy one. And before I talk about distributed algorithms, there's something called the local distributed algorithm. And this is a little confusing because when we talk about sublinear algorithms, we sometimes talk about local computation algorithms and we mean sequential. But there's this local model in caps in distributed. And if you haven't seen this before, there's a couple of things that could be confusing. So I just want to clarify. So something that's probably not confusing, if you think of distributed computation, you probably assume, okay, there's some processors and there's some links that they communicate on. So that part makes sense, right? And it's probably not too big of a step to say, okay, let's assume the maximum degree of this network is D and it's known to everybody. Okay, that so far seems okay. Here's the part that was surprising, and this is also not surprising. Communication round. In each round, each node can send a message to each neighbor. Okay, again, not too surprising, it seems okay. Here comes the part that, that I found surprising when I was first looking at distributed computation. The network graph, the communication graph, is the input graph. There's no other graph written up in the sky and everybody gets to look at it. It is the input graph. So they're computing on themselves. Okay, so that's something you need to keep in mind. When a distributed algorithm in the local model is solving vertex cover, it's solving vertex cover on the communication graph. Okay, so that's one thing that could lead to confusion if it's not clear in the beginning. Okay, and the other thing is, what do you want at the end? At the end, after k rounds, each node is not going to know the full vertex cover of the whole graph. All it's going to know at the end is whether I am in the vertex cover. Okay, that's all we know. Is that clear? So this is the model. Oh, yeah, you know what? Good. Let's assume that every node gets a unique identifier. That may be that's not always the case in distributed algorithms, but let's just assume that everybody gets a unique ID. So everybody knows its own name. But what I know, like after the first round, I might know the unique IDs of my neighbors. And after 2 rounds, I may know the unique IDs of my neighbors' neighbors, and I might know who has edges to who within 2 steps of me. So I may know the complete graph, like I may know BFS up to stage 2 after 2 steps. And I'm not bounding here any kind of communication. So people could send me everything they know. So at this point, we're not doing that. All right. All right, so now, there's an interesting observation of Parnas and Ron that has led to a lot, well, it's a connection between local distributed algorithms and sublinear algorithms for oracle that use these oracles. And these are sublinear query as opposed to sublinear time. Usually they give you sublinear time as well, but what's guaranteed by this reduction is just queries, okay? So here's the connection. If there's a k-round distributed algorithm for vertex cover, what does that mean? That means for any node V, after k rounds, it knows whether it's in or out of the vertex cover, okay? Well, if it knows after k rounds, that means its output can only depend on the inputs. This means the unique IDs, the neighbors, the randomness, whatever, and the computation of a k radius ball around V. That's all it can depend on. Okay, so just think, if I have a one-round distributed algorithm, what can happen? All I can do is get any kind of message from my neighbors. That's all I can get. And those messages that my neighbors sent me, they had to send in the first round, so they haven't heard from their neighbors yet. So it can only depend on their local information that they started out with, okay? After 2 rounds, my neighbors already got some information from their neighbors, okay? And they can send it to me in the second round. So at that point, I know everything up to 2 steps away. In k rounds, I know everything up to distance k, okay? And that's the most I can know. Anything k plus 1 away cannot reach me in k rounds. All right, so that means a sequential algorithm, okay? A sequential algorithm to figure out what V is gonna output just needs to look at this radius k ball around V. It just needs to explore the graph, do a BFS up to k, distance k from V, figure out what's around there, and then compute the value that V would have answered. It can simulate the distributed algorithm, figure out what everybody would have done in round 1, what everything in the k minus 1 ball would have done in round 2, what everything in the k minus 2 ball would have done in round 3, and so on until the kth round. Well, all I have to do is figure out what would be output at this point. Okay, that's all it is. Okay, so I just need to simulate all the computations only in this ball. And how many nodes are there in this ball? Well, the degree of the graph is bounded by D, which I think I use delta here. So let's say the degree of the graph is bounded by delta. So I can have at most delta to the k nodes in this ball. And I just need to look at the information in this delta to the k places, and I can simulate everything by myself. Okay, so you may ask, maybe the simulation is complicated. That's true. So all I'm claiming right now is a query bound, not a computation bound. But usually the query bound gives you usually if you follow this reduction, the running time is just fine. Okay? Questions? Okay, so this seems like obvious, right? But it really led to a lot of algorithms. Why? Well, it is exponential in k, so that might worry you. But there's been major improvements in local algorithms in distributed computation. So there's really been, over the last, I would say, okay, maybe it's 15 years, but there have been kind of dramatic improvements in how fast you can solve things in constant time in distributed algorithms, okay? And it's really impressive what they can do. And there's a lot of things that they can solve super, super fast. In particular, this work of Kuhn, Moschibrota, and Wattenhofer gives a distributed algorithm for all LPs that are either, I think they do packing and covering. I think they do all packing and covering LPs. They give you an approximation, and the running time is something like log D over epsilon, I believe. So I don't remember exactly what their running time is. What I know is it yields, using this Parnas-Ron reduction, it yields a D over epsilon to the order log D over epsilon sequential time algorithm for vertex cover, for approximating vertex cover using this method, okay? And what I want to say is there's lots and lots of other fast distributed algorithms. I'm not going to describe them today, but I just want to say there has been major improvements in this area. And this includes packing and covering problems, matching, maximal independent set, coloring. And so, and there's actually interplay between distributed algorithms and sublinear time algorithms now. So many papers actually have results in more than one model. Also, if you're interested in massively parallel computing, even that model. So there are several papers in recent years which come up with a new technique and make improvements in all three models: massively parallel, distributed local, and sequential sublinear time. Okay. All right. So just to recap here, what's happening is there's a T-round distributed algorithm for vertex cover that gives a Dmax to the order T sequential query approximation. And the way it goes is you sample the vertices of a graph, simulate the distributed algorithm to see if each of these V's are in the vertex cover, and then output the fraction of the sampled nodes that were actually in the vertex cover times n. So that's kind of the plan. All right. And this kind of idea has been used on a lot of problems. Okay. Questions on that? Actually, I think the place to ask questions would be more like here. So I just want to say it's a big paradigm, and it's one of the major ways. Okay. Method number 2 is to construct oracles by simulating the greedy algorithm. Okay, so now I want to talk about how you can approximate vertex cover via maximal matching. So this is kind of known. That the nodes of a matching, any maximal matching, gives you a pretty good vertex cover. In fact, any maximal, it doesn't have to be maximum, any maximal matching gives you a vertex cover that's no more than twice the value of the optimal. Okay, so I'm not gonna prove that right now, but I'm just gonna hope you've either seen it or remember it, or if you don't want to remember it, you can think about it later. Okay. All right, so let's talk about maximal matching. Let me talk about the sequential greedy. I'm not worried about sublinear time for this slide. For this slide, this is not sublinear. This is just a standard sequential greedy algorithm for maximal matching. What do? Your matching starts out as the empty set, and we're just going to keep adding edges to it. Okay? And what we're going to do is we're going to go through every edge in the graph, and when we reach edge uv, if neither u nor v have been matched previously, we're going to add this edge to the matching. So it's very greedy, right? And then after we've gone through every edge to see if we can add it, I have uv. Can it be added? If neither u nor v have been matched yet, I can add it. So I'm going to add it. And then I'm going to go to the next edge. Can I add it? No. Okay, so next edge. Can I add it? Yes, no, whatever. And I go through every single edge, keep trying to add these edges. It might not be the biggest matching. It's just going to be maximal as opposed to maximum. Actually, why am I with this? Forgot to take it off. Sorry. So, okay. So why is M maximal? Okay, if UV is not in M, then either U or V had been previously matched by an earlier edge. Okay, so this is really going to give you a maximal matching. So the issue is now, which order should you go through these edges? Greedy doesn't care. Greedy is going to work no matter which order you go through. All right. So we're going to assume there's some sort of rank that tells me which order to go through, and any way of ranking the edges works. Okay. So I'm just going to assume there's like some kind of rank that tells me the ordering, and that's what I'm going to use. And any rank would work. It won't give me the same maximal matching, but every ranking order will give me a maximal matching. Okay, now why can local algorithms hope to simulate the behavior of greedy? Well, an easy case would be that if an edge has smaller rank than all of its neighboring edges, like let's say my rank is 1, I'm the first edge, I don't even need to look at my neighbors. I know that they haven't been put in because I'm the smallest rank, so I have to go in, okay? So we know that if an edge has smaller rank than all its neighboring edges, greedy definitely puts it into the matching. Okay, why? Because we're looking at the edges in order of rank. Okay, so I'm looking at 1 before 2, before 3, before 4, before 5. Okay, so now let's say I'm edge number 8, and my neighbors are 10, 11, and 12. Well, I know that I was considered first by greedy 10, 11, and 12 hadn't been considered yet, so they couldn't have been put in. And therefore, I know I must go in. Okay? We'll see, and I'll do another example. All right. So now to decide if edge E is in the matching, I need to know what happened to all the adjacent edges that came before E in the ordering. Okay, I need to know if they're in or out of the matching. All right, but I don't need to know anything about edges that come after. All right, and the problem is an arbitrary edge order can have really long dependency chains. So what about this edge here? This edge here, so here, 112, all right? He's next to 113. Greedy considers 113 after he considers 112. So I know that at the point that 112 got considered by Greedy, 113 was not put into the maximal matching because it hadn't been considered. But 111 had been considered. I have to figure out if 111 is in the matching. Well, for 111, 111 doesn't need to worry about 112, but 111 does need to worry about 110, okay? And 110 needs to worry about 89. 89 needs to worry about 88, and so on, okay? So this has long dependency chains because to figure out if 112 is in the matching, even if I knew it was a line, I need to know if I'm an odd or even number of steps from the beginning. So even if you told me everything about the graph except like exactly where am I on this line, then I still need to go down this whole line and figure out, am I an odd or even number of steps? So you can see here that it's non-trivial, even though I think that just because I have this ranking, I can try to figure out locally whether I've been put in the matching or not. It's not so simple. I may have to go spend linear time to figure it out. Yeah.
We only need to know about the neighboring edges, right? Why do we care about all the...
What's that?
We only need to care about whether neighboring edges are okay.
Right, but to figure out whether my neighbor is put in, the neighbor needs to look at everything ranked less than the neighbor.
But we have already considered whether they are put in or not, even before considering this edge, right?
So in the sequential algorithm, that is not sublinear, you go through the edges in order. Now what I'd like to know is, I'd like to know if this edge 112 was put in by the, okay, so there's the global algorithm that looks at all the edges in order, okay? That is not sublinear time because it goes through all the edges in order. Now, okay, now I'm in a different situation. I'm edge 112. I want to know, did Greedy put me into the matching or not? And I want to figure this out in sublinear time. Can I figure that out in sublinear time? On this graph, no. On this graph, I cannot figure that out in sublinear time. But the question is, do I have hope? Okay, and this was a nasty ranking. But what Nguyen and Onak showed is that if you gave random rankings, all the dependency chains are likely to be short. Okay, in fact, very short. Okay, now, so if you give random rankings, Greedy is still gonna work because Greedy doesn't care about the ordering. Greedy just works. Greedy needs an ordering, but it works. But the important fact is that if you gave everybody a random rank and used that as the ranking for Greedy, then you're going to have short dependency chains. Okay? All right. So this is the algorithm of Nguyen and Onak. We're going to assign a random number to every edge in the graph. And now when I get asked, is edge E in the matching? Okay, that's the question. Do I have to go through the whole graph to figure it out? And what they say is, no, you don't, okay? What they're gonna say is, find all the adjacent edges to E in this graph. And actually, I'm gonna do an example. Maybe I'll do it now. Here, okay. Let me describe what the algorithm is, and then I'll do it. I'll do a run, okay? So I'm asked whether E is in the maximal matching, okay? Let me go through all the neighbors of E that have smaller rank and figure out recursively if they were put in the matching or not, okay? If any of them were put in the matching, then I know that I cannot be put in the matching, so I output no. But if none of the preceding edges that are neighboring to me were put in the matching, then I would have been put in the matching by the Greedy algorithm. So I put myself in and I output yes, okay? So that's the idea. I can somehow figure out locally. All right, so let's do an example run. Okay, let's say we got queried about this question mark edge right there. And these are some ranks. Let's pretend those are random, okay? All right, so I had rank 0.5. We're gonna pick random ranks by picking just random numbers between 0 and 1. Okay, so let's say that guy got named that guy got 0.53. I look at all his neighbors. Okay, so this neighbor is smaller. This neighbor was considered earlier. This neighbor was considered earlier. This neighbor was considered earlier. This neighbor was considered later. So this edge is definitely not put in by greedy yet at the time when the global algorithm considered 0.53. Okay, so just what we're trying to do, there's a global algorithm that does greedy in order of the ranks, and we're trying to emulate it by a local algorithm that just looks in my neighborhood to figure out what the global algorithm would have done only on this edge. Okay, and so the global algorithm would not have looked at 0.87 before 0.53, but it would have looked at all three of these neighbors. So let me try to figure out, is 0.22 put in the matching? All right, so to figure out if 0.22 is put in the matching, I have to look at 0.22's neighbors. Now 0.22 is less than 0.53, so 0.22 would not have worried about whether 0.53 was put in the matching, but 0.22 does need to worry about these two neighbors. 0.71 is bigger than 0.22, so that definitely was not placed in the matching before 0.22 was considered. But 0.08 is smaller than 0.22, so I have to figure out, was 0.08 put in the matching? So let's recurse on 0.08. And 0.08 is really now becoming a very small number. Every time you go down pretty well. And so then 0.08 is next to some pretty big numbers, 0.79 and 0.54. Okay, so 0.08 is smaller than every one of its neighbors. Okay, so when the greedy algorithm considered 0.08, it was the first one to be considered in this whole group, and therefore it had to have been placed in the maximal matching. Okay, is this clear? All right, so 0.08 had to have been put in because, and I'm talking now the global greedy algorithm, the one that works in linear time or whatever, would have put this guy in because it wouldn't have seen these edges yet. So this guy gets put in the matching. All right, that means 0.22 cannot be put in the matching because it now has a neighbor. So the global greedy sequential algorithm would have put 0.08 in and therefore could not have put 0.22 in. So that guy was not put in by the global algorithm. So the global algorithm so far doesn't have a reason not to put 0.53 in, at least not because of this edge. So these two edges would not be reasons to not put 0.53 into the matching, but we have to check these two also. So let's check them. So 0.37 is also smaller. So I don't know, was 0.37 put into the matching by the global algorithm? Let's say that these two, these two were ranked bigger than 0.37. And so yes, it was put in by the global algorithm. And therefore, 0.53 cannot be in the matching. Okay, so what we're doing is we're somehow trying to figure out what this global non-sublinear time algorithm would have done without actually doing all of its computations, just doing the part that we need. Okay, is this clear? Like questions? Any questions? Yeah. Oh, okay. I'm going to give you, this is great. I'm going to do the analysis right now. But so far, do we agree that it works? Sort of. Excellent. Some people agree. So that's good. Okay. All right. So why does this actually work? We'll worry about the running time in a second. But it works because greedy works under any ordering of the edges. So if we give it random ranks, it's going to work. Okay. And now this is going to estimate. It's going to output, okay, this, like, don't worry about this second bullet. Let's not worry about that. Okay, what I want to claim is the expected number of queries to the graph per oracle query is exponential in the degree, but no dependence on n, the number of nodes. Okay, and the main idea is we can bound the probability that any path of length k is explored. because when you look at a path of length k, the ranks have to decrease along the path. Okay, you only remember, if you remember in this example, any path we looked at, it had to be because the ranks were decreasing. We never looked at things where there was, once we looked at 0.22, we never looked at 0.71. We could only look at edges that came before 0.22. And when we went to 0.08, we could only look at edges that came before 0.08. Okay, so these edges along this path have to be decreasing. Now, what's the probability that on a path of length k, the edges are all decreasing? It's 1 over k factorial. Okay, so the probability I look at any path is at most 1 over k factorial, but there might be a lot of paths. So we have to balance out the fact that there could be a lot of paths to the fact that the probability of any single path is really small. Okay, so so we just said the probability of any given path of length k being explored is 1 over k factorial. Now, the number of neighbors at distance k in this graph, this is where we're using the degree bound, is at most the max degree d raised to the k. Okay, so the expected number of neighbors explored at distance k is just d to the k over k factorial. Okay, so for each neighbor, there was some path to it, it has to be decreasing. So it's at most d to the k over k factorial. And the expected number of explored nodes is at most summing over k from k equals 0 to infinity, d to the k over k factorial. And this turns out to be e to the d over d. So the expected query complexity, multiply that by another factor of d, because you have to look at your whole adjacency list, but whatever, it still ends up 2 to the order d. Okay, so this is something that's independent of the number of nodes in the graph, as long as you have bounded degree. Okay, or I guess if you have d equals order log n or something, then it's 2 to the, so it's going to be 1 less log. So you, as long as you so you can handle really small degrees, even if they do depend on n, as long as they depend really small compared to n. All right. This is not the best you can do. This is the thing I can prove in the lecture. But there, you can do better, in fact. For example, if you always recurse on the least ranked edge, then there's been a line of works, which has just been shows that if you recurse on least ranked edge first, then you get something nearly linear in the degree. Actually, I'm not sure about this work, which just came out. I don't know what algorithm was used here, but this gives you nearly linear in the degree. Okay, so you can get, what am I saying? Is it nearly linear time in the degree? Yeah. Yeah. So this actually goes from exponential down to nearly linear in the degree. So the running time is no longer exponential in D, but not, and these guys get to polynomial in the degree, and there were improvements, and this gets to nearly linear in the degree. Running time to estimate this. So it's still sublinear even for graphs that don't have bounded degree, because it's just going to be nearly linear in the expected degree. Okay. All right, so that's simulating greedy. There's more complicated algorithms for other problems, such as max matching, set cover, positive LP, and lots more. And a big OO. So this is actually not an open question here. So I mixed that up. So ignore that, okay? That's not an open question. We know nearly linear. There's another model where this is still maybe an open question or may not be, I'm not sure. But let me just say, I guess for, so let me just say that in general, the area here has a problem with dependence on degree. So for specific problems, sometimes we have polynomial in the degree, but for many problems we don't. And so it's kind of pick your favorite problem, check if it's been done. Usually it hasn't, and try to get polynomial in the degree is usually a good way of finding a good problem to work on. Okay, so most of the time we don't. Okay, now I wanted to mention there are classes of graphs where we can get even better results based on things called partition oracles, such as hyperfinite graphs. Hyperfinite graphs are these really cool graphs where they're kind of the opposite of expanders. So instead of being highly connected, they're highly disconnected. You can you can delete epsilon fraction of the edges, epsilon times d times n edges, and break up the graph into tiny pieces of size polynomial in 1 over epsilon. So not even depending on the size of n. Okay, planar graphs are hyperfinite. So there's lots of classes of graphs that are hyperfinite, and for these you can do much better. Okay. Okay, so that didn't take too long. So I have time to talk to you about something called property testing. Were there any questions on this? Yeah. Okay, so I'm going to assume that everybody knows their own rank. Okay, one way you can do this is everybody picks a random number between 0 and 1. And as long as you pick enough bits with high probability, everybody gets a distinct choice. So like if I pick a random, okay, if I pick a random number between 1 and n squared, and then divide by n squared, then I'm going to get a number between 0 and 1. But the probability that any two processors pick the same, or any two I and j pick the same number, is very unlikely, right? So what we could do is assume there's some sort of random oracle, like a hash function or something. There's just some, let me assume there's just some random bits that tell me that I have access to, kind of random access to. So let me assume that there's some random bits and I have access to, and I can just see what is the random bit for node I, what is his random rank, and what is the random bits for node j. But I'm going to pick enough random bits so the probability that I and j have the same label is very, very small, even if I union bound over all pairs. I think Ming wanted to add. Okay, so.
But so long as each edge is allowed to pick its own randomness, you can just do it lazily with the defect, right?
I think you do need to be consistent. Wait, so one thing you can do is you can use log n wise independence. Ning, what were you going to say?
Just saying that you can generate a number
Yeah, so I think this is true, and then you should write it down to make sure you use the same one. Okay, that's the easiest. Yeah, I think that's the easiest answer. And yeah, so just generate the bits and write it down whenever you use it so that you stay consistent. If you ever run across this edge again, you should use the same bit. Okay, but it's a good point. This question is good because it's like an issue that comes up. There are other models at which we implement this type of algorithm, the greedy, and there you can't write things down, and you have to remain consistent with people that don't even see what you write down. And there we have to assume, for example, log n wise independent random bits and things like that. But so here it's writing.
I guess like the random 0, 1 number is the placeholder for random permutation.
Exactly.
So as soon as you see a new edge, you just have to insert it in a list of things you decide on. But then all of a sudden your main goal is for sublinear-time algorithms, and it doesn't. I mean, the other things are related to the distributed computation, but it's clear it's a sublinear.
Right. Yeah, here there's no distributed right now. Right. Right, that's right. You can just write it down. Is there a question?
Yeah, first off, it's not clear that we need a single ranking and we'll be computation over the random orders of rankings together. But my question was whether there are any parameter regimes where we're more interested in sample complexity than computation complexity. You want to stay on one edge and do multiple simulated edge permutation rather than picking the edge.
I don't know of any such, but it's an interesting question. Yeah, I don't know. Yeah. Was there some other question? Okay. All right. Yeah. Oh, sorry, yeah? There's one up there and one here. So guys, pick. Okay, let me go up there first and then you'll get to you. Yeah.
This is more of a general question, but if you compare the global algorithm and the distributed algorithm, where exactly is the time saved?
Where's the time what?
The time at stake. The one has dependence on the other one doesn't.
Sorry, I'm hearing half the words. Say it again.
Where do you save time? If you use this.
Oh, here, why is this faster than the distributed? Ah, that is a great question. So good thing there's only 4 people on the Zoom because I'm going to make a picture. Okay, thank you for that question. So Parnasran says, okay, to figure out this answer, I have to look at this whole ball. And what this one says is, I'm actually going to look at something like this. And this may be smaller than that. And that, I think that's the picture that is the best to think about. Why greedy can sometimes save. Okay.
Thank you.
Yeah. Other questions? Your question.
Oh, so what improvement do you get for hyperfinite?
Oh, way better.
I mean, what how so? Like,
Actually, way better. When I say way better, it's way better historically, but I don't know if currently.
because somehow the fact that you can get these Pauli in the average degree implies a lot of nice things with planar too, right?
Yeah, and actually the hyperfinite, the partition oracle is actually quasi-Pauli in the degree. So it actually isn't an improvement.
Right. I mean, I'm just wondering if it's still an improvement in light of the fact that that's not a good question.
Okay. Thank you, Ankar. Everything I'm telling you today is a lie, but it's kind of interesting anyway. So Ankar makes a good point that these partition oracles are quasi-polynomial in the degree, and this is polynomial in the degree. It's linear in the degree. Then, I mean, the new result it's linear in the degree. So maybe these partition oracles aren't actually better for hyperfinite graphs. Maybe you should just use the newest results instead of these. And that's interesting, and that's probably true. That's a good point. Thank you. Okay, but still there are these oracles for hyperfinite graphs, which I urge you to learn about because they're just interesting, not just for vertex cover, but for other problems where we don't know how to solve things in linear in the degree. Does that make sense? Okay, thank you. Thank you for keeping me honest. Thank you. Okay, all right. So if there's any other question, or I go to property testing. Okay, so property testing is a different model. Everything we've talked about now is a sublinear time approximation algorithm of a number. Okay, it's like there's some combinatorial optimization problem. It's supposed to output some number, and we give a 1 plus epsilon plus multiplicative approximation or a 2 multiplicative approximation, and then we have this additive error, and that's what we're outputting. Okay, property testing is for problems that are decision problems. So the output is 0 or 1. How do you actually approximate 0 or 1? I mean, what are we going to do? Output 0.9. So then we could just say 1. I mean, it's not clear what we mean by an approximation for a decision problem. So what we want to do is think of inputs that have the output 1 as inputs that have the property. Okay, so maybe the problem is the graph bipartite? It's a yes/no question. There's no approximation here. Is a list in sorted order? Yes or no? Okay, so what we're going to say is no, it's not just a yes/no question. There are inputs that have the property. There are inputs that are far from having the property. And then there's kind of this middle range of inputs that are kind of close to having the property, but don't quite have the property. And what we're going to say is these purple guys in the middle there, you can either say they have the property, which is kind of close to the truth, but not quite. Or you can say they don't have the property, which is true. They don't have the property. And this leeway on this purple set is going to allow for much faster algorithms. Okay, so the fact that I'm giving you this leeway on these kind of close is helping. All right, why would you allow that? Well, it's sort of a natural question. It might be just as good if your data is constantly changing anyway. yesterday I asked you, I started with the question of whether the graph on the world has, the social network graph on the whole world has diameter at most 6, and it's a yes/no question, but you might as well ask, is it the case that the graph has diameter 6, or that it's very far from having diameter 6, meaning that a lot of new edges need to be inserted into the graph in order to cut down the diameter to 6. Okay, and we talked about that at the end of yesterday's lecture. So that might be a reasonable question. It also may be a way of getting a fast sanity check. You can rule out all the really bad inputs quickly and then spend your extra processing time on the inputs that pass the test to check if they're really good or just close to being good. But it might allow you to cut down a lot of processing on the bad inputs. And it's also related to this model selection problem in machine learning. Okay, property testing is a kind of old field, and it's been, I used to think it was new, but I think I've aged, and so has the field. And so it's been studied on functions, on strings, on graphs, on matrices, on code words, you name it, people have looked at it. I mean, well, maybe not. So there are probably still a lot of open questions here too, but it's been looked at in a lot of settings. Whenever you define a property testing, you have to define what you mean by the representation of the object and what kind of queries you allow on the object. So the complexity of testing whether a graph is bipartite is very different depending on what you define. Like, do you define it as the distance matrix and are close to having the property means you're allowed to change epsilon fraction of the entries of the distance matrix? That's epsilon times n squared different locations. Or do you define being close to bipartite as I'm defining my graph as an adjacency list representation, and you're allowed to change epsilon fraction of the edges, and that's epsilon times the max degree times n, which is very different than epsilon n squared, okay? So testing bipartiteness for matrices with epsilon n squared distance is constant time. Testing, is that right? It's constant, it's independent of n time. Okay, but for degree d-bounded graphs, it's root n time. There's a lower bound of root n and also a nearly matching upper bound. Okay, so things can be very different depending on what you're assuming about your data, how it's represented, and also what you define as close and far. Under, usually the distance metric is kind of standard, like you get to add or remove edges for graphs, but what do you mean by close? Do you mean epsilon times n squared? Do you mean epsilon times d times n? And these can really affect whether it's doable at all in sublinear time and how fast. Okay, so I want to talk about a simple property tester, and I'm going to talk about sortedness. Okay, so this is like a type of monotonicity testing. I'm giving you a list of numbers, y1 through yn, and the question is this list sorted? Okay, so this clearly, just to figure out exactly if it's sorted, you have to look at everything. But what we want to test is if the list is close to sorted. Okay, so the query complexity is going to be measured in terms of the list size, but what we want is some running time that's really small compared to the list size n, and we're going to go for c times log n. That's the goal. So logarithmic in the list. And what do we mean by close to sorted? We're going to say a list of size n is epsilon close to sorted if you can delete at most epsilon n values to make it sorted, otherwise it's epsilon far. So like here, this input list is sorted. This is close to sorted because if you delete 2, 39, and 21, the thing is in sorted order. And this thing is far from sorted because you have this decreasing sequence, so you can keep at most one of them. So we're going to keep that guy, and there's another decreasing sequence, and basically the biggest monotone sequence is that. Okay, so that's far. So you want to reject this guy, you want to accept this one, and this one you can either accept or reject, whatever you want. All right, so, okay. So again, so we're looking for something where our probability of success is at least some constant, like 3/4, and we can just boost the probability of success arbitrarily high by repeating several times. And if we ever see fail, then we're just going to output the thing. I mean, we're going to output fail. And if we never see fail, then we say, okay, this one I'm going to take a chance and output pass. Okay. All right, and now the claim is we can test this in order 1 over epsilon log n time. But first, let me show you some attempts that don't work. Okay, so here's a proposed algorithm. Let's pick a random location in the list and check that it's good with its neighbors. So it's like if I'm going into a library, I'm going to send, the student and tell them go to a library book, check that the library book the random library book you looked at and its neighbor are in the right order. Okay, and now all the students come back to me and say everything I saw was in the right order. Can I say this thing must be sorted? And the answer is not a good idea. Okay, why? Because you could have, here's a bad input type. Let's say we'll take, I'm going to just demonstrate it by numbers instead of book titles, if you don't mind. But let's say take this list, 1 through n over 4, 1 through n over 4, 1 through n over 4, and 1 through n over 4. It's just repeated 4 times. Okay, now pick a random location. 3, its neighbor is 4. It's great. Look over here. 52, and 53 are going to be in the right order. Anytime I pick a random order, unless I fall on one of these borders, the neighbors are going to look great. What's the probability I fall on one of these borders? 4 out of n. That's it. That's not good, right? So this is a terrible test, right? We ran that. Here's another. This is the one most people suggest if they usually I'm really nice and I say suggest a test. This is the one people suggest. Pick 2 numbers and check if they're in the right order. Okay, so let's pick random I and j. Let's assume I is less than j and check if yi is less than or equal to yj. Okay, here's why that one doesn't work. Let's take n over 4 groups of 4 decreasing elements like 4, 3, 2, 1, 8. So basically 4, 3, 2, 1. All of these are going to be bigger than all of these, but they're going to be in decreasing order. All of these are going to be bigger than anything that precedes it, but in decreasing order. So it looks, so 4, 3, 2, 1, 8, 7, 6, 5, 12, 11, 10, 9. Okay. Now, if I pick random I and j and they're in different groups, everything's going to look great because between groups, if I'm in this group, if I'm in 2 different groups, then I'm going to be in order. Okay. In order to see a problem, I have to pick I and j in the same group. What's the probability of doing that? Not so great. If I pick lots of I and j's, I'm going to have to pick root n samples until I'm likely to see a group collision. Okay, so I'm going to need at least root n indices until I get 2 indices in the same group, and only when I see that will I see a problem on this particular input. Okay. But you could say, well, this input, if I looked at neighbors, I would know there's a problem. Okay, so somehow we have to combine looking at neighbors and looking at faraway things. The previous example, the problem was if I had looked at faraway things, I would have seen a problem, but I looked at only at neighbors. Here, I look only at neighbors, but I look at only at faraway things, but if I had looked at neighbors, I'd be all set. So clearly, somehow we're going to have to mix up the distances of the pairs we look at. Okay, and that's what we're going to do. So actually, the first way to solve this was just let's pick all possible distances. Let's bucket distances, distance 1, distance roughly 2, distance roughly 4, distance roughly 8. We'll pick those log n sets of distances, and then pick 2 things that differ by roughly that distance. Okay, and that was the first way of doing it, and that had a messy analysis. So I'm going to show you something easier. Let's do binary search. Binary search, you start out in the middle, then you go distance n over 4 away, right? Then you go distance n over 8, then you go distance n over 16. And by the time you're done with that binary search, you've tried basically within a factor of 2, you've tried all the distances. Okay, so let's do that. Wait, what did I say? Yeah. Before I discuss binary search, I want to make one minor simplification. I want to assume that the list is completely distinct. Okay, and I claim that is not a big simplification. That's an assumption, but it's not really an assumption because this is kind of an old trick that I first saw when I was learning about parallel algorithms in the 80s. I guess I'm dating myself, but I am kind of, this is a known trick, how to make a list distinct, because you can virtually append I to each xi. Okay, so if I have the list x1 through xn, in my head, I'm going to think of xi as being xi comma I. Okay, so if you're 2 and I'm 2, you're 2 comma I and I'm 2 comma j. So what this does is, you see, so like two people, this is 1, 1, and this becomes 1, 2. And if there was another one down here, it would be 1, 10 or whatever, okay? This breaks ties without changing the order. So now my list is distinct. And this is all we're doing implicitly in our heads, okay? All right. So what's the test gonna be? We're gonna do the following thing 1 over epsilon time. We're gonna pick a random I. Okay, look at the value, so the random index I into the list. Look at the value at that location in the list, y sub I. Now, that's a number, okay? Forget where you found it for a second, okay? It's just a number. Do binary search for that number. And hope you found yourself back to location I. Okay, so in this case, because we did the transformation, it's actually gonna say y sub I comma I. So I'm gonna do binary search for y sub I comma I. But, and now, while I do the binary search, I need to make sure that it was a legal binary search, that when I went left, my list got smaller. When I went right, the numbers got bigger, okay? If I see an inconsistency in the list, the thing isn't sorted, reject, okay? If I don't end up at location I, there's a problem, reject, okay? So that's what we're gonna do. If I see any inconsistency or I don't end up at location I, we fail. Otherwise, we try again, and we try order 1 over epsilon times. So the running time of this test is order 1 over epsilon times log n, because I need log n for the binary search. Okay, why does this work? Okay, so the running time we're okay with, right? It's logarithmic, 1 over epsilon times log. Why is this good? Let's say that index I is good. If when I pick I don't see an inconsistency. When I went left, I got smaller. When I went right, I got bigger. And I ended up at location I. Okay, so we're gonna say it's good if binary search for y sub I is successful. And if we want to restate the test from the previous slide, what we did is pick order 1 over epsilon indices I and pass if they're all good. Okay, and according to this notion of good, the binary search was successful. All right, so why is this good? Well, if the list was sorted, then all the I's are gonna be good, because you're always gonna, when you go left, you're gonna get smaller. When you go right, you're gonna get bigger, and you're always gonna end up at location I. This is where we use the fact that we made things distinct. Okay, all right. Now, what I wanna show is the opposite. If I'm far from sorted, why does this thing fail? All right, we're gonna show the contrapositive. We always do this in property testing. I mean, we a lot of times do this in property testing. Instead of showing that if we're far from sorted, we're likely to fail, we're gonna prove that's P implies Q. We're gonna prove not Q implies not P, equivalent, right? So we're gonna prove that if we're likely to pass, then we must be close to sorted. It's equivalent, right? Okay, so it's contrapositive, that's okay. So if we're likely to pass, then the thing must be sorted. That's what's left. And what I mean by likely to pass, at least 1 minus, close to sorted means at least 1 minus epsilon fraction of these n's, of 1 minus epsilon fraction of the indices are good. Oh wait, no, that's not what I want to say. I want to say we're close, but if we're likely to pass, then at least 1 minus epsilon of these fractions must be good, because I tried, you know, I took 1 over epsilon samples of these I's and I checked that they're all good. So if the test is likely to pass, it must be because the fraction of I's that are good is very high. I didn't see them in 1 over epsilon times. So that means there must be at most epsilon fraction of bad I's. Do we agree? Okay, this is just simple sampling right now. Nothing fancy. I didn't even use Chernoff, okay? Good. Now the main observation is if 1 minus epsilon fraction of these I's are good according to this definition of good, I want to say that there's a large increasing subsequence. And the way we're going to do that is say, look, any pair of good elements but, must form an increasing, must be in the right order. And so if I have 1 minus epsilon times n good elements, then they must form an increasing subsequence. Okay? All right, so why is that true? Why is it if I take a pair, I and j, they're both good, why is it the case that yi has to be less than yj? Okay, so I have a pair, I and j, let's assume I is the smaller one. I want to claim that y sub I is also less than yj. And all I can assume right now is they're both good. Okay, well, any ideas? Yeah.
The binary search, considering first degrees.
Yes, yes, exactly. So when I did binary search for I did binary search for j. They start out in the same place. At some point they split, okay? They split at k, okay? Now when they split at k, I went left. So y sub I is less than y sub k. J went right. So y sub j is greater than y sub k. And therefore y sub I is less than y sub j. That's the whole thing, okay? All right, so pairwise, any two good elements are in the right order. If I take a whole group of good elements, they're all in the right order. They're mutually in the right order. And therefore, these 1 minus epsilon n good elements are all in the right order. And if I just delete the epsilon n bad elements, I'm left with a very large list that's monotone. So this original list was close to monotone. Okay, that's the whole thing. Okay, questions? So, okay, so the running time was order of 1 over epsilon log n. And then this thing definitely accepts good lists and with high probability rejects bad lists. Okay, and the probability statement came in here. Maybe I was unlucky and there were a lot of bad elements, but I didn't see them. But that's very unlikely. All right, questions? You guys must be exhausted. I'm supposed to be done. Yeah, question. Exactly, exactly. Okay, so yes, this can be made, first of all, yes, it can be made non-adaptive. And even this particular algorithm can be made non-adaptive. Because if you notice, once you pick an element I and you do the binary search, you know exactly where that binary search should go. Like once you pick a sample, you know exactly where the binary search should go. So before you actually look at the list, you know exactly where you need to look and what places need to be consistent before you actually even look at the list. So this can be easily made non-adaptive. Okay, it's true though that binary search is thought of as adaptive. It's just that I know where it's supposed to go. So this particular thing can be made non-adaptive. Okay, so I guess I just wanted to say in closing, these examples are just the tip of the iceberg. And there's lots of cool results that are going to be presented in this workshop Wednesday, Thursday, Friday this week. And there's some great speakers. I'm very excited about it. So I hope you all want to come. And that's what I have to say. But which slide? Tell me when to stop. More? These? Okay. Sorry, to go, sorry, I am hard of hearing. Yeah. So you mean like that this one is greater than here?
Yeah.
So global would not have looked at 87 before 53. Yeah, actually here. oops. You mean here, like, there's nothing smaller before 37? Is that the answer? Is that what you're thinking? What's this number? Oh, sorry, let me come up in here. What is the meaning of the numbers? Oh, these are the random ranks. Yeah, these are the random ranks. So there's just, I'm assuming you picked random numbers between 0 and 1. Yeah, okay, sorry, I'm just not good. Thanks, okay. Any other questions?
Maybe it's a question in the second to last slide, when you search for the least common ancestor or something, how did you know that yi things were yi?
Oh, assumption. I assumed without loss of generality that I mean, I have indices I and j. Oh, okay, wait, so you're asking, I just want to make sure I have the right question.
It's just like the punchline, very end.
Here.
Yes.
Okay. When I searched for I, if it was a good search, there was some point at which the searches for I and j diverged. I by assumption is less than j, just because one of them has to be smaller. Okay, now they were both good. So when they went on their binary search, they went left when they went smaller and went right when they went bigger. Now they started out, everybody starts out at the midpoint when you're doing binary search. And then at some point their searches diverged, but they both reached where I reached index I and j reached index j. I'm using the key y sub I and using the key y sub j. Okay, so at some point y sub I went left and y sub j went right. At that point, y sub I was less than the node, the key at the node, and y sub k was greater than the key at the node. And that's why I know y sub I is less than or equal to y sub j. Is that good? Okay, you're welcome. Yeah.
Just follow that question. Since you know that y sub I is less than y sub j, how do you continue the program? Why do you know that that's what the order will be? You will be success shows that the probability is true.
Okay, so I know y sub I and y sub j are in the right order. So pairwise, every pair of elements is in the right order. So now the question is, why is it that, I mean, I have a whole bunch of these i's and j's. Why are they all in the right order? Okay, so if they're not all in the right order, there has to be some pair that's out of order. And I'm saying no pair is out of order. Okay, yeah, good questions. Great, thank you. These are like subtle points that after you think about it, okay, you say, but until you think about it, it's like, why should that be? And so ask the question, because everybody's online. Okay. Anybody else?
Question.
Yeah.
So the first two attacks you mentioned were coming with the different counterexamples. I was wondering, is there a quick example that can refute both attacks?
Oh. Yes, there is. So it would be something that okay. Okay, what it'd be is I'd go up for a while and then, so let me just show a picture. It would look something like this. So the general lower bound, there's a lower bound that shows you need log n, and it looks something like this. And then you have another thing up here. And then you keep going up, okay? So now, so most things are in order with their neighbor, but you have to be in the same group to see a problem. And also you have to, okay, I don't want to really describe the lower bound right now, but basically you choose these things so that the chance you go from here to here is really low. But most of your queries are either in one of these or between these guys. And if you use little o of log n, there's some kind of range of distances that you're not using, and you fit this so that the mess happens during that range of distances. But it's going to be too hard to explain right now. And I think everyone's exhausted. And we have 3 days of workshop that you guys need to go to. Okay. Thanks.